thank you for the invitation, and sorry not to be with you. So if you have yet another Zoom workshop or talk. Another thing, I realized that you had already like a bunch of speakers talking about twisted layer graphene and all of that story. So what you will see today is very the basic notions, how we go to the basis of background model. And actually, I will work with Yao, so it will give you a lecture more about the fancy part, and I will go through the basic notion today. And also, in twisted layer graphene is already like a broad topic, and my lecture will solely focus on the insulating phases. And all this work, if you're interested in, can be found in these massive 6 papers that were published like a year ago with all these people in the picture, not all of them, but a large fraction of them. And I should give credit especially to the students, Fangxi and Lisa Fakti and Shiba Song. We also have Zhao and Yan that will give you 2 other lectures on that same topic. And since then, we have more work on the story, and we have support from Dimitri Kaligaru, Pascal Vambek, the theory side, and the experimentalists led by Aliasan. And if I have time, I will talk a little bit about this other reference and maybe some upcoming work, depending on which I have. Okay. So at this stage, I think I really don't need to convince you that all the story of wiry superlattices into the materials in testing 1, especially from the theory point of view, because we would like to have a system where we can engineer the alliance of topology and strong interaction, and hopefully maybe at a temperature which are a bit hotter than what we have for atoms, not exactly still from the realm of chemistry, where these data are the hot evolution, but something else, determined intuition. Also, if you're interested, I strongly just to get this quick overview of Mars superlattices, you can have a look at this reference down there. And once again, what I was mentioning is really what we know from that topology, and the typical example that you have in mind is the Landau levels, but it requires an external magnetic field and strong correlation. And that's basically what all the story of just bilayer graphene will give us. But as usual, in terms of theory, when you have flat band and strong interaction, it's always a complicated system because you cannot say, well, I can look at the interaction as a perturbation compared to the activity relation. And that's why, for example, it's capturing the fraction of effect, which is one of the example of strong correlation and topology. People use several tools like model wave functions or numerical calculation to try to investigate these systems. So that's the price you have to pay when you deal with the flat band and strong interaction. And that's something I'll also address in the next lecture tomorrow. And as I said, you already know a lot about graphene and that you have a wealth of rich quantum phases emerging. And this lecture will be solely about coordinate states. So today we will focus on single particle physics. As I said, I will derive this molecular model from this lecture, and Joe will talk more about the symmetry and the topological properties of the model. And tomorrow we will start to crack up the interaction and focusing on the specific state, try to provide some analytical derivation or analytical model that capture the insulating phases. As usual, when we propose some answers for quantum ground state, you have to compare to experimental results. And that's what I will try to do also tomorrow, on Friday, sorry. Okay, So let's start with the basic stuff and basically graphene. So if you already know graphene or the BM model, please feel free to do something else and wait for the next lecture. But if you've never done the calculation, I will try to show you how it works. So we start with the honeycomb lattice with two carbon atoms. Per unit cell, right? And you have a picture of the lattice just right here on the left-hand side. We use blue and green because you have two sublattices which are disconnected. More precisely, it's a bilateral system. So A site in green is only connected to B sites, and the B sites are only connected to blue sites. Of course, we call them A and B, but they are identical carbon atoms. And I'm sure Andre gave you or will give you some lecture about the flatbed models. We will discuss the story of flatbed lattices, what it implies.
This afternoon, stay tuned.
This afternoon, okay. So you will have more detailed derivation of the properties of flatbed lattice this afternoon. Okay, so to be a bit more concrete, what is the distance between two nearest neighbor atoms? Well, the lattice spacing is for the graphene is on the order of 0.142 nanometers. How many electrons do we have per unit cell? So we have one pi electron that will distribute between properties per carbon atom. So the orbitals per molecular plane. So basically 2 electrons per unit cell, but that's including the spin. So it's you're basically half billion. You have 2 sites, include the spin. You can discard, and then so it's you have 2 electrons per unit cell, so you have billion if you take into account the spin. Oops. And we need the lattice vector A1 translattice AX and A2. So EX and Y are defined here in black, and in gray the lattice vector A2 will be half A X minus square root over 2 for the 3 over 2 A. Okay? So really that's the basic definition for atomic magnetics of graphene. Now I can work out the Regnault for graphene. So you know how to get where the critical space you can use the lattice vector B by their properties the lattice vector A1 and A2. We do the same for the orthogonal basis E, the orthogonal basis in the space F. And so B2 will be given by 4 pi over 3A and Y, which is what you have here. And B1 will be given by this expression put down right this way, 4 pi over 3A to Fx. This one out. And when you look at the brilliant zone, you can define the high symmetry points. Ones that typically stay defined for the double symmetry transformation. So you have the gamma points, the n points, and the two k and k prime points, which are the high symmetry point. Okay, so we have the time band model, we have defined what's going on in real space. So now we are ready to compute the block Hamiltonian and get the energy spectrum. So we define the momentum, it goes onto the basis B1, B2. Oops, not. K1 plus K2, B2. The hopping amplitude for the time varying model, if you want to something that matches the actual graphene, can be on the order of 3 electron volts. And you see you have a simple model with 2 atoms per unit cells. As I said, it's a bipartite lattice, so A is only to B and B only to A. This is your unit cell, and it's not pretty straightforward to derive the expression of the block Hamiltonian for this time-binding model. So it's going to be for the A site and the B site. A, K, A2, exponential minus A, K, A1. And the complex conjugate. So your Hamiltonian should be in condition. So A2 plus exponential A1, 2. And you see there is no hopping terms between two A sites. That's why you have 0 binding. And you have to include the amplitude here. And it's just divided in slightly different way, introducing the function f of k. Go to contrast exponential by k a2. This exponential minus k a1. All right. Now we have the Hamiltonian. We can just diagonalize this 2 by 2 matrix. As you see, this matrix only has off-diagonal elements, so the eigenvalues will vary by pairs of plus E and minus E, so you have a particle of the symmetrical spectrum. And we can actually just plot this benchmark structure. It's easy to see that the highest energy that you would have is on the order of, well, is equal to 3 times T. That is the E to minus E symmetry. And you are happy with the services of your image. And of course, what you already know is you have Dirac nodes when you look at graphene and haptic, which are depicted here around the K and the K prime point. And you see that this Dirac dispersion is valid on something of the order of like 1 eV without any trouble. So if you want to discuss the low energy excitations around the Fermi energy, you can basically forget the large fraction of the dispersion here and just solely focus on what's going on around the K and the K prime points. So actually, we can compute the coordinates of these Dirac points. So you see, because you have this particular symmetry, the nodes exactly appear at equal to 0. If you want to look at the position, what you have to do is just to look where this function f vanishes in the Boolean solution. So that's what give you the look at the coordinates of the k and the k prime points. The other, so that's for, let's see, if I did get it right, this is for k prime, this should be for k, I hope for. No, that's the, so k, k, 1, 2, 2. And you can check that if you plug this value of k in f of k, you get, well, just the usual formula for the root of unity. And we have something that would look like this. Which is equal to 0. Like you get 1 plus exponential 2 by the 3 plus exponential minus 2 by the 3. This will be 0. All right. So the energy at k and k prime. And if you want to express k and k prime vector in the nicer orthogonal basis, then you just get, so that's and fx, see that's what you get here and here. And of course you can get the other by getting the reciprocal lattice vector. Okay, so let's go for the position of the k. F prime point, see that indeed the dispersion relation is equal to 0 for the graphene at this location. But what we want is an effective description of the low energy physics around the k and the k prime points. So what you do in that case is just you linearize around. Let's start with k. So say that your momentum is k plus some small deviation. Let's say we focus on k first. And what you have to do is just plot the expression of the function f with respect to delta k. One and 1 plus I delta k a1 plus exponential 2 pi and then k2 plus 2. We're going to do and now you choose the fact, well, at the k points, f of k0, and you end up with, just by messaging the expression, you can regroup it in 2 terms. This one, which is sum of between a1 and a2, and then 1/2 a1 minus a2 times delta k. And if you look at these 2 vectors, they form an orthogonal basis. Indeed, if I show the situation where you have a1 and a2 with a 120 degrees between them, the sum will be like this. So that this is a1, a2, the sum will be like this, while the difference will be like this. compute the norm. These two guys. So the square root of 3 that you have here will make a proper normalization between the data. So you can, with these two orthogonal vectors, what you're able to do is to define a new xy basis. So from A1 minus A2 and A1 plus A2, and if you do that, well, around K, h of K, or just h of delta K, so we won't be able to Hamiltonian here, will look like square root of 3 TA over 2 sigma dot K. That's the Fermi velocity we have, which is for graphene on the order of C over 300. While sigma are the Pauli matrices, sigma x, 1 and 0, and the sigma y here, 0 I minus I 0. So that's the effective Hamiltonian around the K points. Now let's work out the same story around the K point. I will not do the calculation in front of you, but it's the same kind of calculation. The only thing that will differ is the conjugation here for sigma matrices that we have in sigma 1. So basically, you have two Dirac codes. If you look at the low energy physics around the Fermi energy, which are actually rated by Tanner's symmetry, the kind that you have the given Hamiltonian of K prime, you have to conjugate corresponding to K, tells you that they are related by such a symmetry. That's what you obtain. Just this version. So, 0. One at each K points. All right, so that's all the ingredients I need from the graphene installer side. Any questions? And I'm sure that most of you have done the calculation previously, but sometimes new people can install, so I think it's good to at least see some of the derivation ones. Okay, now that we have the story for graphene, we will do what's done is going to do. Then we need to stack together two graphenes of layer and slightly rotate one compared to the other. So once again, you take 2 layers of graphene, you put them exactly on top of each other. So what I mean here, each other, namely A on A, so A side for the A side, and the B side for the B side. So that's the AA stacking. And now what you do is to rotate, let's say, the top layer by some small angle theta. And if you do that, well, the story, you have more structure that you can see on the picture here with much larger periodicity. And if you, so that's by comparing two, when we have yet another AA region, but in between two AA regions, you also have regions where you have a A site on top of the B site, so or vice versa, the B site on top of the A site, which is the A site. From when you do the calculation, it's usually easier to think about the rotation not by rotating by an angle theta, the top layer, but by rotating by theta over 2, the top layer, and minus theta over 2, the bottom layer. So you have expressions which are more symmetric. But physically, it doesn't make any difference. So that was a picture in real space. And of course, you can think about this rotation not in real space, but in momentum space. And that's what I've depicted here. You have K1, well, the PC2, which is in blue, which is the Brilliant zone for the top layer. And sorry, that's right. Yeah. PC1 in blue is the top layer, PC2 is the bottom layer. So that's the rotation, how it's performing, the different rotation of the two graphene Brilliant zone. And of course, since in real space you have a periodicity which is enlarged compared to the one of the graphene, it means that the Brilliant zone of the monoid will be way smaller. And you can actually show that for small angles, the monoid Brilliant zone will be defined is also a triangle lattice, and you can observe here. So you have an hexagonal monoid Brilliant zone. And one side of the hexagon will be exactly given by the distance between the two K points of the graphene. And for the monoid Brilliant zone, all the high symmetry points like the K, the K prime, the N, and the gamma point will have the N sub-index to indicate that they are related to the monoid Brilliant zone and not to the graphene Brilliant zone. If you want to get an understanding why you have this kind of construction for the monoid zone, you can try to do that just in one dimension by taking two periodic system with a periodicity that is very close and try to see that the difference between the two high symmetry points that you have in one T will be related to the monoid Brilliant zone of the one D lattice that you create. That's very interesting. This exercise is pretty nice one to try to grasp how it works and why we get such property for the relation between what's going on for the Brilliant zone and two Brilliant zone for graphene. One thing I never mentioned when I was talking about the rotation, it's not only rotation, not only in the angle, you also need to define where is the center of rotation. Actually, for the lattice, it doesn't matter where you perform the rotation. This will, if you take the center rotation around the AB region, you will get exactly the same result. But where you put your center of rotation doesn't matter. Of course, in the expression, well, the expression might change with the gauge summation. But overall, you can choose freely where you put your center of rotation. So the next question is basically how large is the monoid itself? just to get some numbers or some raw estimates. Once again, this is not a rigorous derivation or anything like that, but just to give some insight how large it is. So we can do the following exercise. Let's say we start from a given AA region. And of course, if you add one matrix vector, let's say from the top, from the bottom layer, if it only goes in that direction, you only have A sites. Right. Now for the top layer, if you go on that line, you only have also A sites. So you will have another AA stacking when you perform a certain number of translation in around A11, and you will meet another A site of the top layer when on top, in addition to all this A11 translation, you perform A12 translation. So if you want to rough estimate, what you can do is exactly put into equations what I just described. So it's basically when do you need another AA region. And you can compute the length, for example, of this black line here. From the angle, and this will tell you something which is on the order of 3 A sine theta over 2. For the small angles, you can simplify the expression and get something like this. Just the pre-factor is not really important here, because that's the, if you compare to the volume or the length of the graphene in the cell, which is called A, everything is divided by the angle theta. So the volume of the molecule cell is 1 over theta squared, the volume of the graphene cell. If you want a more rigorous treatment, you can have a look at these two papers. So they try to put more carefully, or we go from the demonstrate case to the PM model. So let's try to put some numbers here. Let's say we take an angle of 1.05 degrees. If you write that in radians, it's 1.8, where you 10 to the minus 2 radians. This number, this angle 1.05 is special. We've seen that many times. This is the first magic angle of twisted bilayer. So let's say how many carbon atoms we have. Oops. Well, let's do the counting. We have a factor of 2 because we have 2 layers. We have 2 atoms per graphene cell. And of course, the ratio, we have a factor of 1 over theta squared when we compare the size of the graphene cells and the molecule cell. So overall, if you plug all the numbers here, you will get something which is on the order of 5 10 squared. It's 1.2, 10 to the minus 4, and meters per moire cell. So the point is, let's say you want to describe twisted barrier graphene by a tie-binding model, like we did for graphene. Graphene is pretty simple because we have only 2 atoms per unit cell. So at the end of the day, there is only 1 orbital per site. So it's a simple 2x2 matrix. It's fine. If you want to do the same type of calculation, so that is description for a moire system at a small angle, you will have to deal with something like 10,000 sites for the unit cell. So clearly, this is not the route to take if you want to describe a twisted barrier graphene. What you would like is, so since we cannot do the tie binding, and technically, of course, you can try to put that in a computer and still matrices that you can diagonalize, but getting some insight just by some empirical result will be too difficult. So you have to resort to a continuous model. And in any case, if you look at what's going on in real space, so that's the AA regions of twisted barrier graphene. For the angle I was mentioning, the typical distance is on the order of 13 nanometers. So if you compare to the scale of graphene, which just to remind you, the typical distance between the atom is 0.14 nanometers. So we have like 2 orders of magnitude bigger for the moire unit cell. It doesn't make sense to keep track of what's going on for the carbon atoms. So what ingredients do we need? Well, first, we need to describe each layer individually. So for each layer, what we do is to simplify the model by considering only the Dirac flows. So we forget about the full dispersion relation of graphene and we focus only on the effective description around the K and K prime bonds. And for the we will assume no cross-talking. Between K and K prime. So the 2 values of graphene, we assume that decoupled. And that's what basically you observe in momentum space. What you can do is to describe what's going on between the 2 K primes of each layer, or the 2 K prime points. But you will make a separate description for these two regions. So that's the first thing that we need. And maybe the less trivial one is a continuous description for the coupling between the 2 layers. After all, you don't want a boring system. You just take 2 decoupled layers, nothing fancy will appear. So you need to describe what's how the 2 layers are coupled. So that's what we need to describe the twisted barrier graphene. So let's start with point 1, which is by far the simplest. So I did the derivation of the Dirac flows in momentum space, but of course you can write the Hamiltonian directly into space. So you will just replace the momentum by derivative. Okay, so that's a pretty simple statement. And now you have to take into account that you want to rotate the two layers. Okay. And as I said, you get nicer expression by taking the symmetric case where you rotate the top layer by theta over 2 and bottom layer by minus theta over 2. Let's say you rotate the top layer by theta over 2. So of course, this will slightly change the expression if I keep xy basis identical to both layers. So we get just the rotation cosine theta over 2 sigma x minus sine theta over 2 sigma y y sine theta over 2 sigma y sine theta over 2 sigma x, which you can recombine into for the small angle, which is always the approximation that we assume here, like a first term that is identical to the Dirac dispersion in real space without the rotation, and one extra term proportional to theta. That you can write down as the derivative and vector product with sigma. Okay, so that was for the top layer. We can do the same exercise for the bottom layer. And you will get, well, the same start term, and with just a change of sign because you're rotating the other direction. See, here we have a plus, and here we have a minus. So I can write down the part of the magnitude corresponding to the two decoupled layers. If I reintroduce the thermal velocity, oops. So I have first term here and rotation here. 0, 0. Yes, it should be a minus. So in this form, this is the top layer, and this is for the bottom layer. It is usually more convenient to introduce a set of body matrices for the layer index. So that's going to here, tau 0, sigma plus theta over 2, tau z. Relative vector product sigma. So this tau 0 is just the identity for the power matrices. And these are the power matrices for the layer index. While the sigma, the power matrices for the sublattice. Okay. Cool. Once again, that's the easy part of the given problem. It becomes more difficult when you want to describe the coupling between the two layers. And that's really where this is a Mach model it's very useful because they provide a very nice description into the coupling. In all generality, what you want to say, well, the coupling between the two layers, if I write it as a matrix like I did for H0, will be a term that is off diagonal. So that's the expression here with these matrices, TR, and because it has to be Gaussian, it's T diagonal R on the lower, the left bottom corner. And T of R, of course, not only can couple the two layers, but it might couple either A side to A sides of layers or A side and D side. So they also have a matrix structure. And this is a McDonald model. So, well, let's take the simplest expression we can imagine for such a coupling that will respect the symmetries of the model, and that will be given by what's going on when we are exactly at A snapping and at A snapping. And this is the expression that we propose in their model. As you can see, it has a bunch of vector Qj that I will define later, and also a set of matrices Tj, or j going from 1 to 3. And that's the expression of the Tj matrix. Note that we have here sigma 0, so this part couple A with A, B with B. Whereas if you look at sigma x and sigma y, we will couple and And actually, it's very informative to just take R equal to 0 in the expression that you have here and look at what you get for T of R. Remember that here we choose a center of rotation to the AA side. So taking R to 0 is just to get the center of the rotation. And if you do that, your expression will greatly simplify like this. For the same reason that we predict for the function of A is equal to the summation of J. It's the group of unities that will appear and all the terms will cancel out except for this one. And you find back, well, at 0, I have only the coupling with AA and D. So the two parameters, omega 0 and omega 1, this expression actually show that omega 0, what I showed here, that omega 0 is the kind of strength of the coupling between two AA sides or two BB sides. Whereas omega 1 will control the coupling between the A side and B side of different values. So what are the QIs? Well, or the QJ. Basically, these guys will enforce periodicity that you need. Because you have a change of lattice. And they are related to the monoganism. It's basically what is depicted here. Q1 is the one that connects the K points of the bottom layer to the K points of the top layer. So Q1 connects K1 to Q2. You can actually compute the norm of Q1, so norm of K1, the norm of K2, 2, 4, 5, 6, 7, 8. Show up the 1 and 2 index. Just do a little bit of trigonometry. That's what K1, K2, that's K1, but the angle of theta, yeah, that's angle of K1 is 2K sine theta over 2, which is the small angle we just wrote. And now you can get Q2 and Q3 by just performing a 2 pi weekly rotation or 4 pi weekly rotation. Q1, Q2, and Q3. Just by 160 rotation. So if you want some order of magnitude, for W0, so the coupling parameters W0 and W1. Let's say, for example, if you want at some point to compute the band structure of the model, but you really need the Perry velocity. This one, the proper unit, taking h pi equals c equals 2 pi equals 1. It will be given by 5.3 even per angstrom. And W1 will be given by 110 even. So that's what you will find the reduction. We will use a lot in the next lecture the ratio between omega 0 and omega 1, because knowing the exact ratio between these two quantities is not completely straightforward, and you will see the literature. This one is on the order of something like 0.6 to 0.8. And basically, what you have to keep in mind is omega 0 is always smaller than omega 1 due to the correlation effect. But that gives you like an order of magnitude of these quantities. Okay, now that we are done with the FAT model, we need to compute its band structure. So, as usual, let's simplify the problem first, and then we introduce the ingredients step by step. So let's say first we discard terms due to rotation. We go derivative vector product sigma and the coupling TR. The first thing you have to do is you have the dispersion relation of graphene, even though it's simplified with the one of just Dirac code. You have to start from this dispersion relation defined in the graphene Brillouin zone to the Moiré Brillouin zone. Another way to phrase it, what you do here, well, you pave your momentum space with the small Moiré Brillouin zone. So paving the graphene band structure, the graphene Brillouin zone, with Moiré BC, it's equivalent to take the dispersion of graphene and fold it within the Moiré Brillouin zone. And that's basically what you've depicted here. Let's say that's the full graphene, easy. And the two dotted lines here say, well, that's the size of the microansel. Of course, remember, I said that the angle in radians is on the order of 10 to the minus 2, so it's an exaggerated size for the microansel. But basically what you do is you take your interact code and you fold it within this one microansel. That's what you obtain on the right-hand side of the left side. One thing that you have to keep track of, well, is which bands you're looking at. So you have to define the band index, which is just to say which copy of the right zone you're actually looking at. Okay. With that in hand, we can give you the expression of the BN model, but this time not in real space, but in dimension space. So this is the BN model in its full glory. That's the expression written in second quantum rotation. And the matrix element H Q prime is defined. So let's break down this expression. We have K, which is defined in the microansel zone, so that's the momentum in the microansel zone. We have a first term that comes from the Dirac dispersion. But you see, it's not on K, you have a shift by minus Q, and I will show you soon this Q will just tell you which copy of the microansel you're actually looking at, which is equivalent to which band you're looking at. Now we have another term, which are these are the contribution coming from the rotation. The psi here will take two different values depending on this here. So Q and Q primes are two vectors. They are defined by this lattice of primes. The blue is the Q plus lattice, and the red is the Q minus lattice. And psi equal to +1 if Q belongs to Q plus and -1, Q belongs to Q minus. Anyway, this is nothing like this. This is basically the fact that the top layer and bottom layer they are rotated with opposite angles without and minus coverage. And this expression here, the last term, is the interlayer coupling, which does written slightly different way. Remember that what we need at some point is to know which band we are, which is equivalent to say which copy of the microansel we are. But in this expression, there is no notion of layer index. So actually, this lattice of points, Q plus and Q minus, Q plus and Q minus, will include both properties. Once again, we need to encode both the layer index and which copy of the NDC, which is the band index that you can fold in. So if I zoom in here, one, two, and two, three, and 7, shoreline with two additional lattice points. The whole circle is the top layer, while the field dots are the bottom layer. Remember, I was mentioning that Q1 connects the two K bonds of the first layer. So Q plus is what they call the top layer, and Q minus is the bottom. And actually, if you do both, with Q plus and Q minus, you will be encoding of both properties I just mentioned before. That's why, for example, here it's for the dynamic dispersion, it's just the shift to track of the band index, but you still have one for each layer. Whereas if you look at T-shape, you know that you have to couple on different layers. So that's why you have the delta Q prime, that's the minus Q shape, because you need to couple on the Q from the Q plus to the Q from the Q minus, Q prime from the Q minus, or vice versa. Here I don't mention how I center this lattice. This momentum lattice. You have two different ways to center it. You can center it either here at the beginning of point, or here around the K point. And we'll discuss that in a few minutes. I think I still have 10 minutes, right? I'm almost there. Perfect. Okay, so now we have the expression for the B-hand and current written down in momentum space, and we can look at the band structure. We have several parameters that we can tweak. Let's say the velocity is fixed. We fix W1, and we will only play with two parameters, namely the rotation angle and omega 0. So let's first fix omega 0 to be like 4.8 times omega 1. And just change the angle theta. And you see, we start from a situation with small angle around 0.95 degrees, and we'll crank up. We'll increase the value of theta. Around the steering G, you have two flat bands emerging, but which are still connected to the other bands. And once you start increasing theta, you see that the gap opening around the gamma points, and the gap increases until you reach a value of 1.45, where it gets one of the flattest bands you can find, and a pretty large gap between the two active bands around the steering machine and the bands below and above them. You barely see that here you will have two bands. If I increase the angle, then the bandwidth of these two bands will increase. And I don't have a higher angle, but at some point you will also close the gap, and at least you will also use the length of the band. And that's why the oil pipe is the magic mineral. It's where we will add in the flex band. And we'll discuss how to find this in those. So that was the effect of theta. We can also look at the effect of omega 0 on the band structure. So once again, we keep omega 1 fixed. We are exactly at the magic angle with 1.5 degrees. And we start from the situation from 4.8. And let's say we do something extreme, and we just discard the top beam between two AA lines. And as you see, you don't change much the structure of the content of the band structure. You still have rough flat bands, and actually we have increased the gap. It's a different story if you would have taken the situation where you take omega 1 to 0 and just consider omega 0 to be the 110 millimeters mentioned. Here we get a situation where all the bands are connected. This story will be quite important when we discuss application tools in space, because there are many nice properties that you get when you have omega 0 equal to 0. And since, at least from the monitor, I can find the situation is able to connect it to a more entangled omega 0s. There are lots of insight that you can get by looking at this limit first. So, a more practical question. There are many young people that I'm sure that at some point, if you work on this kind of system, your advisor will ask you to actually compute numerically the band structure. And it's important to both in terms of analytical model that you can derive or actual implementation in the computer, to deal with the sum over all the statistics that in principle is an infinite lattice. So how do we practically compute the band structure? What I mean here is the infinite sum. As I said, your momentum lattice can be centered around different points. I mean, it's just a matter of choice. You will find especially two different convenience centering. One is around the gamma point, and the other one is around the k point. Let's focus on the first one, so the center at the gamma point, so the leftmost one. You can organize your summation by taking shells. You see, we have a first shell of points here, then you have another one here, and so on. So when you write your Hamiltonian, which is going to be massive, because remember that you have all that your biagonal is theta square, theta square, smaller than the one of the graphene. So it's going to be a massive matrix, but you can organize your calculation where you take, well, let's say it's what's going on by taking the momentum points in the first shell, so shell 1, shell 2, shell 3. And your Hamiltonian will have a very nice block diagonal structure. So this is the shell. We have coupling, coupling thing, which is just 2 points of the shell 1 coupled to 2 points of the shell 1. We have all the block, coupling points of the shell 2 with one of the shell 1, and vice versa. Another diagonal block. But as you can see, there is shells are not connected, shell 1 is not connected to shell 3 by any of the Q1, Q2, and Q3. So this block is 0. So now we have the shell 3, shell 2, shell 3. So you have a tridiagonal structure for the Hamiltonian, which is pretty convenient because it means less storage, and also it's a pretty efficient way to find what's going on for the flat band analytically. So actually, how can you find the magic law? Well, once again, you go back to the paper of Mr. McEnroe, and they say, well, what you should look for is you should look at the velocity at the clearing point and try to tune theta to make it match. But velocity adds your relation. So if I look here, for example, what I would like is to get something which is pretty flat around the K point. And how to get, so that's one way to do it like with a computer. You can just do things like this. But you can also get a pretty good approximation by taking the lattice of momentum points, as mentioned here, and taking the simplest case. So you can discard all the shells, for example, here, except the first one. Or in the other case where you center on the K point, you can solely focus on the first 4 points. The first one is for the tripod model. You center around the lattice center around Km. So that's what I keep from this input summation. And with that, you actually find a pretty good value of the magic angle. You should actually take the other option, so center around the gamma point and keeping 6 points in the summation. This one is the lattice center around gamma m. You get the magic angle property, and actually the full flatness almost everything. Only the gap, which you get the full flatness to them. And as a last point, once again, here, if you do the calculation with any software, you cannot perform the input summation, even though you can reorganize your term properly. So how many terms? How many points you need to keep in Q plus Q minus? Well, you have the answer most here. It tells you that if you take on 6 points, you get a pretty good approximation. And after 4 or 5 shells, everything will have converged. And there is a good reason for that. I'm sure that many of you did the calculation of the edge mode of the SSH model. The SSH model is way simpler, but the Hamiltonian have also tried the structure. And I'm sure that you have done the exercise of high-speed computing or evaluating the edge modes and see the exponential position of the edge. But here it's the same story because of this logarithm or triangle structure for the determinant. If you start with a very good approximation captured by the top block on the top left side of your matrix, then all the other blocks will just give you exponentially small correction. Of course, deeper you go, the smaller is the correction. So basically, with that kind of relation to organize your lattice properly, everything will converge exponentially fast with the number of shells that you consider. right? And just to finish, the two numbers I didn't quote are, if you take what's going on at the magic angle, what are the energy scales in place? Well, typically the bandwidth is on the order of 1 eV, while the band gap is on the order of 14 eV. So that's basically the number that you have to keep in mind for the non-interacting band structure of optical sheet at the magic angle. So you see if your interaction are not too strong compared to this 13 eV, it's going to be a good approximation to solely focus on the two active bands, which are almost flat, and forget about the other bands when it comes to discussing the effect of interaction close to zero. All right, I'm out of time, and the next story will be about symmetries, topological properties, and Pierre will give you the lectures today.
Great, that's a perfect place to stop.